I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
Space. Time.
brain,
Life. The universe.
If you were in space without any protection, what would kill you first? And despite getting closer to the sun, why does it get colder the higher up you go? This week, it's our science Q&A time. I'm Kat Arney, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
So it's time to meet our team, and with me today are Andrew Holding, he's a biochemist at the University of Cambridge. Adam Townsend studies the mathematics of chocolate fountains, I'm sure among other things, at University College London. Caroline Steele is a physicist and a science communicator from Imperial College. And David Rothery, well known to Naked Scientist listeners, who is a space scientist from the Open University. So let's kick off, and we'll start with you, David, actually, and a question from Prasad.
Can we see remnants of the moon landing with telescopes and prove it happened?
This is a big one. You know, people say, did it really happen? What can we see?
Well, of course it happened. You can't see it from the Earth. There's some very nice pictures you can find on the internet if you go to the Lunar Reconnaissance Orbiter website, but that's NASA, so they're obviously part of a conspiracy. So.
Clearly.
But seriously, from lunar orbit, you can see footprints and vehicle tracks and the spacecraft landing sections still on the surface. The Chinese claim to have seen some of the Apollo landing materials on the surface, and the Indians, with their Chandrayaan-1 orbiter, saw the disturbed soil but didn't have sufficient spatial resolution to actually see the hardware. But nobody doubts it happened. The Soviets at the time weren't saying the Americans are cheating. Everybody in the business agrees that lunar landings happened. But you can't see it from the surface of the Earth. The moon is 250,000 miles away. It's too far away. You can see the space station orbiting past, but that's thousands of times closer.
And it's like shiny.
Shiny and big.
Yeah, exactly. I've got a question here for you, Caroline. Let's start with some physics. Nozinle asks this question.
Why does it get cooler as we climb higher if we're getting closer to the sun?
Firstly, the sun is 150 million kilometres away. So actually climbing up a mountain or sort of moving a little bit further away from sea level is really quite negligible in comparison to this 150 million kilometres. So that in itself shouldn't really have an effect on temperature. But it does get colder as we increase in altitude. There's lots of ways to look at this, but one way to think about it is as air rises, it feels less pressure the higher up it rises. So it expands. And to expand, the gas must do work. And to do work, it must lose energy. And therefore, the individual gas particles have slightly less energy. And the definition of temperature is sort of the average energy of these molecules. So if the molecules have less energy at a higher altitude, there's a lower temperature.
So basically, temperature, something that's hot, it's all the molecules are like squished together and they're moving a lot, and that's really hot. Yeah. And then if you're going up into space, the air just kind of goes, whoa.
Yeah, exactly. It spreads out, and by spreading out, you have less molecules with less energy and therefore a lower temperature.
David.
What Caroline's describing is the lower atmosphere, which is probably what the questioner is asking about. But you get above the troposphere into the stratosphere, it starts to get warmer again, because that's where ozone molecules are absorbing solar ultraviolet energy, so it does get warmer. Then there's another layer beyond that called the thermosphere, where the temperature is officially thousands of degrees. But you wouldn't feel hot if you were there because it's almost a vacuum. It's just the energy of individual molecules. It's absorption of solar photons that
so
shake
really
up the molecules.
They're
going for it, but they're so few and far between. There's a high temperature, but almost no heat.
And then when you get out of the atmosphere, then you're really in trouble.
Yeah.
So what would you sort of feel if there was a thermometer there? Would it have a high temperature or a low one? Or does it sort of depend where it is? Is it near the molecules or not?
What, a thermometer filled with mercury or something? I don't know. Depends how you define temperature. The molecular temperature is hot, but you would feel cold. You would need to be wrapped up really, really warm, apart from being almost in a vacuum. Anyway.
Problem in itself.
We can return to that kind of question later. Thank you. Andrew, how about this one for you?
Hello, my name's Tommy. I was just wondering how our vision stays smooth whether we're walking or running. Does it have something to do with our eyes, or is it the way our brain processes the information?
I have wondered this.
I went and looked this up a little bit earlier, and there's kind of two ways of dealing with this problem, and actually were both mentioned in the question.
And if you're a camera nerd, you may have come across two ideas, optical stabilization and digital stabilization. So the first one, optical stabilization, is the idea that the camera has something in it that means the lenses and the sensor all move as you move along. And that kind of takes the bumps out. So you see them with steady cams where you have these big rigs. So when the guy walks forward, the whole camera stays still.
So it's kind of like suspension for a camera.
Well, your whole head can do that to some extent. Your eyes can stay fixed on a singular location and you can move your head around. So if you take a bird of prey and you have it on your arm, if you move a bird of prey around on your arm, its head stays absolutely still. It's quite hilarious because you can move it around really quite viciously and the head will stay exactly still.
So they're just like locked on.
Yeah, I mean, eventually, presumably, the bird of prey will get annoyed and fly off.
Peck your own eyes out or something like that, yeah.
And then the other half is this idea of digital stabilization. So the way a digital camera does that is it takes a bigger picture than it needs, and then as the image moves around, it sort of centers on the same point and just throws away the external information that it doesn't need. And your brain can do that slightly differently because you've got your ears telling you about motion. So as the image moves around, your brain sort of says, well, I know it's not really moving. Of course, the problem with that is if you're in a car and you're not looking at where you're going, your ears and your eyes are telling different things, and your brain goes, there's only one thing that can be happening right now, and that's I've been poisoned. Because evolution hasn't yet caught up with the invention of cars, and that's why we then get really sick.
Does anyone else get travel sick?
Yeah.
My daughter gets very travel sick.
It's the worst. I've just got worse and worse and worse as I've got older. So it's like my ears and my eyes getting worse. And they're talking to each other less.
So there is a thing that as you get older, you get more dizzy. So if you're a young kid and you're on a roundabout, you can do that and go round, around, around and walk off, and it's hilarious. And you do it when you're in your 30s and suddenly you feel really ill. I've never heard of people doing it in their 60s. Maybe there's people out there who are still able to do it and still going strong.
If any of our listeners, please do it safely. If you would like to put your elderly relatives on a roundabout and report back and compare them with younger children, that would be really great. Here's a question for you, Adam.
If the Earth's rotation is slowing down, was it windier in the distant past? If you spin a planet faster, you increase the wind speed. Since we know the Earth is slowing down its rotation, what was the wind speed on Earth in the past?
That is a great question. What do you reckon? That's sent in by our listener of Edgeworth.
Yeah, I thought this was an absolutely terrific question. So the Earth is slowing down because of its gravitational interactions with the moon. So every time the moon goes round, it affects the tides, robs the Earth a little bit of some rotation. I can tell you exactly how much it's slowing down. In fact, we lose about 2 milliseconds from the day every 100 years.
Yeah, I suppose over millions of years that's going to add up.
Yeah, in fact it does. So if you are interested when we're going to get 25-hour days, 200 million years, not long. Anyway, to wind. What causes wind? Wind is caused by warm air. So the air on Earth gets heated up by the sun, the air rises, and this causes a pressure difference, right? Because the hot air has gone up, and so cold air needs to be sucked in, and it's sucked in from the North Pole or the South Pole where it's colder. So you end up with this circulation happening. But it's complicated because the Earth is spinning, right? And so this is the famous Coriolis force. So if you sit on a spinning chair and spin yourself around and you throw like a tennis ball in front of you, the tennis ball seems to sort of veer off to the right. And so this confuses things because it means that the wind isn't directly going from the North Pole or the South Pole to the equator. And what I think is the absolute most interesting, despite the fact that we have these areas of high pressure and low pressure, and you would think, therefore, the wind goes from the high pressure to the low pressure. It doesn't. It actually, wind travels, because of the rotation of the Earth, wind travels along lines of constant pressure. This is why you have isobars on, like newspaper
the little
weather
lines
reports.
when you see,
Yeah, from the 90s, right?
They've been replaced by little arrows now because we're too
yeah.
stupid to understand isobars, I think.
Right. But yeah, it turns out wind goes along these, and this sort of drops out of the maths of the Coriolis force. Anyway, was it windier in the past is the question. And the answer is it's complicated because lots of things affect it. I mean, if you're so continents slow down wind, right? If we're standing right here and you want to go back millions of years, well, obviously the buildings are going to make some effect. How much land there is around us, wind goes slower over land because of friction.
So basically, there's lots and lots of things that could have made a difference, and we don't really know. We don't know if the dinosaurs were like, woo, blowing around.
So in the question they ask, if you spin a planet faster, you increase the wind speed. I'm not convinced. I think there are lots of things that affect wind speed. The effect might, in fact, go the opposite direction. You can get planets that go around very, very slowly, like Venus. Venus has a day of 116 days. It's really slow. And
I don't want to go to Venus and find out if it's windy up there. I think
200 miles an hour.
Wow. That's the wind on Venus. Wow. Yeah. Okay. So it doesn't seem to matter. Okay, Andrew, here's one for you. We've had a question on Twitter from Paul James. He says, I pick my fingernails a lot and leave them all over the world. You disgusting person. How long do they take to disappear? Or do they?
One, yes, you're right, but it's disgusting. Do not do this. Some poor person's having to clean up behind you around the world. It's keratin that makes up your fingernails, so that's actually quite hard to break down. It's not something that biology really has evolved for, to live off fingernails, which is I'm kind of grateful for. So if you ate them, you couldn't digest them. So people aren't going to be eating them. Not many things in the world do really, so they'll sit around for a while.
And there are mummies with hair and nails and stuff like that.
Yeah. So I was at the British Museum recently, and my daughter was looking at this mummified corpse. It was mummified because it had just been sat in the desert. It wasn't an Egyptian one. And she just said, oh, Daddy, it's still got hair. And I had to explain to her that it was actually a person who sat there for 5,000 years.
Ew, David.
Well, I'm a geologist, and I know keratin is a molecule which fossilises. You can extract fossil molecules of keratin from dinosaurs. So we're talking 150 million year old keratin. I don't think fingernails would survive that long, but the stuff of which it's composed can be found in the fossil record.
Wow. That's certainly... do you know if dinosaurs ate their fingernails?
They probably ate other dinosaurs' fingernails.
They would have had claws,
yeah.
Which is kind of similar.
And feathers.
Claws and feathers. Okay. So don't leave your fingernails around the world is the upshot of that one, I think. Thank you. You're listening to The Naked Scientists with me, Kat Arney. With me today are space scientist David Rothery, physicist Caroline Steele, maths guru Adam Townsend, and biochemist Andrew Holding, and they're answering all your science questions because it's Q&A time. If you'd like to send us a question, it's chris@thenakedscientist.com, or you can tweet us @nakedscientists, and we'll do our best to include it in our next show. Now, let's have a question for you, David, which will make us all feel a little bit depressed because Paul has asked this one.
What will end life on Earth first? The sun becoming a red giant and engulfing us, or the magnetic core cooling?
Paul is saying the magnetic core of the Earth is cooling down. I think what he's getting at is the outer part of the core is fluid and electrically conducting, and that's where the Earth's magnetic field is generated. And if a planet no longer has a magnetic field, it's not protected from the solar wind and the atmosphere can be stripped away. If that were to happen, it would be an uncomfortable place for us to live. But Mars has no magnetic field, and we still regard it as habitable for microbes. So even if this happened to the Earth, it would not end life on Earth, Paul. So if you're a microbe, you can relax.
Okay.
The core is cooling down at about 100 degrees per billion years. It's got a way to go. It's got several billion years before it would solidify. I can't tell you how long because we're not quite sure what it's made of. So we don't know what temperature it will solidify at. But the sun is going to swell up into a red giant in 4, 5 or 6 billion years, and that's going to make the Earth intolerably hot for any kind of life, no more liquid water. So to answer the question, for any kind of life at all, the sun becoming a red giant is going to kill off life. If the question is about multicellular animal life at the Earth's surface, maybe the magnetic field collapse will do that first, but we don't actually know.
Andrew?
Yeah, I've heard that the magnetic poles can reverse as well earlier.
Yeah, I was going to ask about that. It comes up in the news, like if the poles flip, where our atmosphere will fly away and we'll all be stuffed.
No, but the Earth's magnetic field has reversed many times. It gets weaker, then builds up again in the opposite direction. It happens every few 100,000 years at irregular intervals. So it's happened so many times, and life has just carried on through. No signs of mass extinction events every time the poles flip.
I wonder about what about things like our communications networks and stuff like that? Is that going to cause a problem?
Well, it may well cause a problem because, So no Pokemon, no civilised life. Won't be protected from the solar wind directly. Technological life could be very interesting in the few hundred years when the field is collapsing and rebuilding, yes.
Wow. Caroline, let's have a question for you from Marianne.
How does fresh water ice, like in the Arctic, form from salty ocean water?
That is a great question.
Yeah. So I learned something new when I was looking into this. So it turns out that icebergs themselves are actually just glacier fragments. They aren't ice that forms from the sea freezing. That's called sea ice. So icebergs are freshwater because they come from glaciers, and glaciers are compacted snow, so therefore they're freshwater. But when the sea freezes and forms sea ice, this ice is also fresh because freshwater freezes at a higher temperature than saltwater. So for a kind of similar reason, that's why we put salt down on the roads when it's cold to stop it freezing over and our cars skidding in the morning.
So the ice forms and sort of pushes the salt out of it?
Yeah, the salt ions are kind of forced out of the lattice.
Andrew?
Yeah, so this distillation process is actually quite interesting because if you get cider and you throw it on the back garden in Canada, the alcohol gets pushed into the core as the ice freezes around the outside. So to distill alcohol in your back garden, it's not going to be a good product, but it's the same effect.
I'm sure in Terry Pratchett books they do that, and it's called scumble, if I recall correctly. We've had a question in here, which I'm going to take now, from Andy Watts.
Is human evolution going in the wrong direction? We have evolved over millennia through a process of survival of the fittest. With medical advances over the last century, many of us, me included, are surviving childhood illnesses that would have previously finished us off. We then reproduce and the genes are passed on. The gene pool must be getting weaker, making us more prone to the very illnesses we are trying to treat. I often hear debates about the science of gene modification, and mostly the arguments are focusing on the negatives and the fears of abuse. However, I never hear the counter-argument that our genetics are already being altered indirectly by human medicine.
That is a great question, and sort of you have to be very careful because there is a word for trying to engineer the human gene pool. It's called eugenics, and it doesn't really end terribly happily. I've been talking to some people about this, and they say, well, you could argue, yes, it's bad for human evolution if you're keeping these things in, but at the same time you're keeping a whole load of other stuff in as well that might be useful. So as we have to adapt and change to the changing conditions and the changing world we're living in, there might also be some good stuff in there as well. So it's very difficult to look at one gene or one disease and say that's not good for our gene pool. But what's really interesting is that it used to be when you'd look at families with genetically caused diseases, things like breast cancer is a good example. If people have the Angelina Jolie genes, BRCA1 or BRCA2, you could track families with the disease and look at people with the disease and go, OK, you've got that gene fault, that's what caused it. But now we're starting to look at healthy people because genome sequencing is so cheap now and finding that they have, quote, bad gene variations or gene faults, but they're healthy, they're fine. And people sort of tend to call them genetic superheroes. And it's absolutely fascinating trying to work out, so what else is it in their genome that is causing them not to be ill? So again, it's like when we're thinking about kind of screening out or getting rid of these genetic diseases, that we may be losing other things from people that are actually have these variations but are healthy. Andrew? And also, for some diseases, it's entirely futile because they're spontaneous mutations anyway. So they may be genetic once it appears in the population, but things like Huntington's will appear even if you haven't got a parent with it sometimes. So you can't entirely remove them anyway. David, here's one for you. Musa has asked, can humans cause earthquakes?
Yes, with qualifications. It depends what Musa has in mind when he says an earthquake. I mean, there are vibrations within the Earth of different degrees of intensity, and people will have heard of the Richter scale. There are 100 or so earthquakes of magnitude 6 or above somewhere in the world every year, like the one in Italy a couple of weeks ago. And there are millions of magnitude 2 earthquakes. Now, how small can you go and still call it an earthquake? Coal mines collapsing cause vibrations which can be detected, sometimes felt by people really close by. Is that an earthquake? I mean, presumably something like a massive bomb going off as well would cause the Earth vibrations to shake. Through the Earth, which you can measure at a certain distance and work out the energy at the source. Fracking is supposed to cause earthquakes, but there's a debate about whether it's causing an earthquake that wouldn't have happened anyway. If you frack close to a fault, you may give the impetus to let that fault move, and the earthquake will happen now rather than in 100 years' time. Is that caused by humans or just triggered by humans, and is there a difference? So it depends on what size of earthquake Musa has in mind, and whether he means cause something which would never have happened, or just trigger a natural event which was going to happen anyway if you'd waited long enough. So it's like many questions in science, a great question, but very complicated to answer.
Fantastic. Andrew, here's one for you from Mohammed, who says, cows eat grass and drink water and produce pure, wholesome milk, which resides in the body close to the intestines. Yet the smell of cows' intestinal contents does not penetrate the milk. How does this happen?
Well, if we just move back from the question and think about what the intestines have to do. So the intestines have to get all the stuff out that grass, partially digested, into the body, but only the bits we want. So they mustn't get out all the bacteria, which could be toxic. You know, you don't want to get it into your bloodstream and get septicemia. You don't want to get any toxins that are on the food. So your gut really is a very, very clever system at only transporting out what it wants. So some of that's done by osmosis, so the concentration of different molecules draws the water out, and some of it's done actively, so energy is expended to pull the food out. And of course, you then have the blood system, actually not a tiny gap before you then end up at the udder, where you make the milk. And of course, the cells there are very carefully putting the right things in that milk, not just anything they come across. So if you didn't have a good barrier with your intestines, you would be getting really sick all the time. So it wouldn't just be getting your milk, it would be getting everywhere. And actually, if we think about the milk for a while, one thing you probably don't think about is you do get infections in udders or in people in breasts, and you get mastitis. And this is a real problem for people who are breastfeeding, because you've got this milk which is very good for growing bacteria. You get these really sore infections, and it's really unpleasant for the mother. And of course, the solution today is just antibiotics. But you do have to make sure you don't get bacteria in there, because they have these horrible side effects.
And also there are some bacteria in milk, and that's presumably why we pasteurise it, so that we don't get sick from drinking it.
Yeah, I mean, but they can come in different stages. They can come in through all the pumps and stuff like that. I mean, what you give to a baby also comes with many of the immunities from the mother as well. So it's a complicated product, milk.
And now, Adam, here's one for you. This is what Morris wants to know.
How do you use light to work out that the universe is expanding?
Wow, how do you do it? With a torch?
With a fire engine, I think, is a better choice. Most of us know of what's called the Doppler effect. So this is when a fire engine or a police car or an ambulance, and I'm familiar with all of these because I live in London, comes straight past your window at night, and you hear it go like "nee-no, nee-no, 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 nee-no," and as it comes past you, that was a great sound effect, right? As it comes past you, the pitch drops, the frequency drops, and the same thing happens with light. And therefore, as the stars move away from us, so I think Hubble actually spotted this. Hubble was looking at sort of nearby stars and sort of spotting what they were made of by looking at their colours. And then he looked at stars that were slightly further away and found that they were sort of similar, but everything was just a little bit more red. And then he looked at ones that were really, really far away and saw that they were even more red. Therefore, he was able to see that everything is being shifted towards the red spectrum. This is called redshift.
Red light has a longer wavelength than blue light.
Right.
So then basically by looking at the change in the colour of light, where it's like the galaxies are going past us going, New.
Yeah, and in the same way that, say, as the fire engine goes past, the frequency has decreased, they found that it went more red, so the frequency has decreased.
You're listening to The Naked Scientists with me, Kat Arney. This week we're answering your science questions, so if you'd like to pose one for our next Q&A show, just send them to chris@thenakedscientist.com. Here is a fantastic question from David.
If you were in space without any protection, what would kill you first?
Let's throw this one open. Andrew, you got any ideas?
So this is absolutely brilliant. You've got to first start, how do you get in space? And, you know, with a lack of a transporter there, I'm going for someone opens the airlock whilst you're taking a nap in it on the ISS. Okay. And then suddenly the pressure drops. And the first thing that's going to happen, you're going to notice it gets a bit cold because we've got the gas expanding again, we discussed earlier. And you're going to also notice that the air's going, which you need to breathe. So the crucial thing to do at this point is you've got to remember not to hold your breath.
That's really hard.
Yeah, well, I don't think so, because if you just think you need to scream, that might be quite natural at this point.
Okay,
yeah,
okay,
so,
airlock's open.
Because otherwise, all that air in your chest is going to want to expand through your chest, and that's not going to be good for you.
Okay, so you would explode from your lungs, Caroline?
You'd also have to be careful to not cry. Because of the lack of gravity, your tears don't fall. They just kind of accumulate on your face and can block your mouth and nose, and you could drown in your own tears.
Would they be frozen, though?
I suppose, would they freeze?
You drown in your own frozen tears.
They boil and freeze. So the low pressure means they boil, but the low temperatures mean they freeze. So you get this kind of microcrystals forming.
So, abrasive.
Yeah,
so maybe
they're
exfoliating.
probably going away from you.
Adam, what do you reckon?
Well, I was going to ask, how much time are we giving ourselves here?
Well, not very long. The door has opened, the air is rushing out. It's like a balloon.
So, but are we talking like we have maybe a minute to live?
So, on the air front, in 15 seconds, your brain will basically decide to protect itself and you'll be unconscious. In about 2 minutes, you'll be asphyxiated.
So we're not worrying about the abrasive effect on our skin of our frozen tears then, because we're going to die because there's nothing to breathe.
Well, if someone gets you in 2 minutes, and if you're outside the ship by this point, you're going to start to get sunburn quite badly. Unless you got high factor sun cream before you did this.
Why would you get sunburnt in space? You always think of it as being like dark and cold. Why would you get sunburnt?
So on the Earth, we have the ozone layer protecting us from all the UV, but you take the ozone layer away and all these things that protect us on the planet, and suddenly you've got raw sunlight on top of you. So you're suddenly going to get a huge amount of radiation on your skin.
As it always reminds me of the joke about like the astronauts who wanted to go to the sun and then thought, well, it's going to be really hot during the day, so let's make sure we go at night. Here's a question for you, Caroline.
How old is an atom of, say, hydrogen?
So that is a very, very tricky question. As kind of said in the question, it depends on what kind of atom we're talking about. It depends on which atom we're talking about. So most hydrogen atoms are 13.7 billion years old, as they were formed in the Big Bang. But if you have a larger atom, it's formed from the fusion of smaller atoms, so it's likely to be younger. But any sort of random atom you pick could be anything from 13.7 billion years old to made the other day in a fusion reaction.
Things like iron and stuff like that, and the heavier elements, they are made in stars, supernovas?
I think they can be made in supernovas. It requires dense, really packed material and a lot of heat to make these sort of bigger elements.
All we had after the Big Bang was hydrogen and helium. The heavier elements are formed in stars and then distributed through the cosmos when the stars throw off material, most famousely in supernova explosions.
Isn't it that Carl Sagan phrase, we are all made of
stardust.
stars? Yeah, star stuff.
True. Yeah.
I think that's wonderful. First time I heard that, I was like, whoa. A question for you now, David, from Donald.
What is the electrical charge of the Earth? Does the planet have an excess or a deficit of electrons, or is it electrically neutral?
Well, I admit to having had to look this one up. It depends whether Donald is talking about the solid Earth or the planet Earth, including its atmosphere.
Okay.
The ground
what are the
beneath
difference,
your
then?
feet does carry a negative charge, and the atmosphere carries a positive charge.
So does that help to keep the atmosphere on?
No, that's gravity.
Right, it's just gravity, so it's not
But
electricity.
it does explain why there are lightning discharges sometimes between the atmosphere and the ground. That's just a current pathway forming that lets the charge neutralise locally.
Okay.
Now, why do we have this charge imbalance? It's very hard to understand, and it's defeating me. But the positive charge on the atmosphere would be because the Earth is receiving charged particles from the sun all the time. Protons, newly formed hydrogen nuclei, to go back to the previous question, if you like, streaming along magnetic field lines towards the Earth, and some negative particles, mostly electrons, streaming along as well. So the charged particles coming past the Earth are deflected by a magnetic field, but some particles, some electrons in our atmospheric atoms, especially the outer atmosphere, are stripped away in this solar wind. And I think that's why we get a positive charge on the atmosphere, because we've lost a few electrons. And I guess the lightning discharges between the atmosphere and the ground sort of locally redress that balance every so often. But it is very, very complicated because we regard the Earth as electrically neutral. That's why you put an earth wire to stop you getting electrical shocks. But it depends what your net positive or net negative charge is measured relative to.
Yeah.
So if you want a safe electrical current going from your socket to your toaster, you want it to be neutral relative to the environment around you, which is the ground. So although that is technically a negative charge relative to the cosmos, it's all the same charge level as your toaster. So you can touch it and get your toast out without getting a shock.
That is a very good idea. So basically, we can't earth the Earth, though, can we? The planet Earth.
You could get a big wire and attach it to the sun, I suppose, but I wouldn't recommend it.
Fantastic question in here from Vincenzo, who says, is there a single food that a human could live a healthy, if boring, life from eating just that one item? And I'm assuming it's like a naturally occurring food, not something synthetic that's got everything in.
For a pizza stagione or something.
Yeah, quattro stagione,
Yeah.
that's all the 4 seasons,
Yeah.
that's got everything. It's a naturally occurring food. Can anyone think of anything?
So, while not completely naturally occurring, a lot of people claim Guinness and bananas.
Guinness and bananas.
Yeah.
Possibly. I'd be concerned about the protein.
And the alcohol level you'd probably have to take in every day would probably have side effects.
Anyone else got a food that they could live on?
I mean, obviously these processed ones exist. Working in a maths office, there are at least 2 people in my office who are trying to survive on just these smoothies of powder and water. And sometimes they taste of strawberry and sometimes they taste of chocolate, and most of the time they taste of neither and are just disgusting.
Oh God! Well, we've done a bit of thinking here, and apparently you could probably live for a little while on just raw meat, uncooked raw meat.
Why uncooked?
Vitamin C is one of the things people often talk scurvy if you don't get enough vitamin C, and it's broken down by cooking and aging. So fresh food is really, really good for vitamin C, and the reason sailors used to get sick is they didn't do fresh food. It's quite hard to get fresh food in the middle of the ocean unless you're fishing, which they didn't do so much.
And presumably, because you can nourish a person with it, human milk. It's kind
probably
of gross.
misbalanced. It's probably misbalanced. It's not the worst choice, but it's fatty. It's got all sorts of things in there for a growing baby.
And not an adult. We've got a little bit of research from the Live Science website, who is a wonderful piece, actually. It's worth looking up because it tells you all the ways you would die if you didn't eat enough things. So without all the right amino acids, they're the building blocks of protein, your hair would start to lighten in colour, your fingernails would get soft, your lean body mass would start to suffer, not just your muscles, but also your heart and organs. Eventually, your heart shrinks so much that you die. So, yeah, don't do that, people. Caroline, can you help out Peter Davis? He's asked us this question. He says, if heat cannot travel through a vacuum, why does the sun feel hot here on Earth?
So we kind of mentioned this earlier when we were talking about ways to die in space. So heat does travel through a vacuum. It just doesn't travel in the normal kind of conduction way that we quite often automatically think of. So for something to conduct, like when you put a metal spoon in a saucepan and it gets really hot, you require particles as the heat energy is transferred through the particles. But heat can also travel through radiation, which is part of the electromagnetic spectrum. So waves travel from the sun to the Earth and heat up the atmosphere. So yeah, heat does travel through space, and it probably would give you really bad sunburn if you were stuck out there with no suit or anything.
So is this why things like you get infrared heating lamps and stuff like that?
That's also radiation, yeah. So it's a different way of transferring heat. It's using heat waves rather than sort of transferring heat through collisions of particles.
OK, that is a great one. And thank you very much, Peter, for your question. Andrew, let's go to the world of biology. I feel there's been a little bit too much physical sciences here. We have a question from Paul.
How does sun on your skin make vitamin D?
How does that work?
So that's a great question. So yes, we need UV to make vitamin D. And unlike a lot of biological processes, it's actually done spontaneously. There's not an enzyme that does it.
So it's like a chemical reaction that's just happening?
Yeah, so it's a specific type of chemical reaction called a pericyclic chemical reaction, and that's where sort of the bonds rearrange spontaneously when the energy comes in the right source, and depending whether it's heat or UV will depend on how the shape of the molecule is after that reaction.
So there's these precursors that we're making, and the UV light comes in, hits our skin, and does the chemistry.
Yeah, so we make a precursor up to a certain point, it's a cholesterol, and then it does this conversion, and then it gets taken on a little bit more to make it into vitamin D.
But that does depend on light actually hitting our skin. So what happens if you don't get enough UV hitting your skin?
So if you're an animal with fur, this is where it gets really interesting. They obviously can't get light to their skin, especially if it's a dark coat. So they actually put in oils that appear on their coat, and that's where it gets UV, and then they lick it back off.
Hang on. So they're making the precursors, they're secreting them out of themselves, the chemistry happens, and they eat it.
Yeah.
That's kind of disgusting.
Well, cats do lick themselves.
I mean, could we don't do that, presumably.
Do you lick cats?
And I don't lick cats. No, don't even like cats very much at all. But what happens, is there actually enough sunlight to make enough vitamin D?
So, I mean, this is a big challenge actually today when we're worried about getting too much sunlight. So if you're inside your house and you're deciding to sunbathe behind your window, you're not getting enough UVB. So UVB is the more burny one because the glass blocks it. So you have to go outside, which isn't terrible. But in the UK, of course, we don't have much sun in winter. So then a whole lot of other things come into play. So depending on your skin coloration. So if you're very pale and you sort of get a lot more UV getting to the parts of the body it needs to get to, then you do produce still not a great amount, but probably enough. If you had a skin that absorbs a lot of UV, you're going to have to probably take supplements.
And you can get vitamin D from food as well. So is it, you're going to need a balance of sunlight and the right food and then maybe supplements in the winter as well?
I think the current advice now is we actually should all be just taking supplements because we cover up with stuff to stop skin cancer, so sun cream. That blocks most of it in summer. So actually, we're not doing ourselves a great favour on the vitamin D front, but we are doing ourselves a great favour on having great skin.
Well, there you go. Avoid skin like a handbag by keeping nice and young and staying out of the UV as much as you can, I reckon.
Yeah, but do get outside because it's great.
I work too hard. You're listening to The Naked Scientists with me, Kat Arney. With me today are space scientist David Rothery, physicist Caroline Steele, maths guru Adam Townsend and biochemist Andrew Holding, and they're answering all your science questions because it's Q&A time. If you'd like to send us a question, it's chris@thenakedscientist.com or you can tweet us @nakedscientists and we'll do our best to include it in our next show. Adam, we've got a question for you from Jason, who I think has been cooking things in his microwave for too long because he asks, how does a microwave burn food? I was led to believe they couldn't burn food, but is this the one where he's actually tweeted us a picture of some burnt bread?
I was unconvinced. So this morning, I did a little experiment. So I brought a little present into the studio.
Okay.
Andy's going to take this now and describe this present.
Kind of small piece of whole grain bread, and on it has a very definite charred mark in the middle, like you've held it against a cigarette lighter.
Can you all smell that here?
Oh, no, I've just got a whiff. Yeah, that's definitely...
It's also very solid and hard.
It is incredibly solid, incredibly hard. That smell, by the way, is the same smell that my flat now completely smells of. So don't try this up. So I put a piece of bread in the microwave for just 2 minutes. And after 2 minutes, the middle just started smoking. And so you get this nice black burn mark.
What has happened? Because if a microwave does work by making the water in the food vibrate, so how can it do something that seems like, a dry fire?
Right, yeah. So, the first thing that happens is that all the water gets evaporated off, so you get loads of steam. Microwaves are sort of set at a frequency that water is very receptive to, which means that water is, heats up. But all of the stuff in bread, in this case, is still getting slightly excited by the microwave energy. So it's just that water is normally more receptive. So you take away the water, what's left? Well, it still tries to absorb some stuff, some of the starch in the bread, for example. And so it also heats up and ends up stinking out your kitchen.
On fire. Yeah. Do not try that one at home. And now we are back out in space with a question for you, David. And Byron has been in touch to ask, why do black holes seem to have more gravity than anything else? Doesn't a black hole have the same mass as the star that it was created from? And doesn't an object's gravitational field depend on its mass? How does that work?
Well, the answer is yes to both those bits at the end. I think the misconception that Byron has is that black holes have more gravity than other objects. It's the strength of the gravity close to the event horizon, which is the boundary of the black hole. If you were to take the sun and magically compress it to the density that it would require to become a black hole, the gravity at the event horizon, the new surface around that, would be extremely strong. But out here at the Earth, we'd notice no difference. So the total gravity around a black hole doesn't depend on whether it's a black hole or not. It just depends on the mass inside it. Now, the sun can't become a black hole naturally. You have to have a mass of, it's the Chandrasekhar limit, which I think is 1.4 solar masses or something, before a star has enough strength of gravity to force its matter into the density required to become a black hole. And there are some supermassive black holes which are billions of solar masses. These are the things, the colliding black holes that were detected by the gravity wave detections. Those are really enormous objects and, of course, have lots of gravity because they've got an enormous amount of mass in. But the short answer is the strength of gravity at a distance from a black hole is independent of whether or not it's a black hole. It just depends on how much mass has gone into it.
Because it's all crushed into a tiny, tiny space.
It's all crushed into such a small space, but the gravity really close to it is so strong that light can't get out, and you couldn't get that close without being ripped apart by the tides.
Wow. We've had an interesting question here in from Facebook from Sean Hoskins, who wants to know, is it possible to DNA test sourdough? Has anyone tried to trace it for bragging purposes, any strain back to its origin? Because I think sourdough, you're meant to leave just flour out and flour and water, and it just accumulates stuff.
So I think it's a natural fermenting, so you don't need to add yeast like you do with normal bread, but that's about as far as I know.
But presumably it's working on microorganisms from the environment.
Well, so a lot of the alcohol you can make without adding yeast is done by the fact there's yeast on the outside of apples.
Yeah.
So I guess there must be yeast somewhere around the place.
Exactly. So, I mean, there's yeasts. Did I see there's a beer that someone's making from Roald Dahl's chair or something weird like that? There are yeasts everywhere. So presumably you could
sequence
sample
the
them and
yeast
sequence them, yeah.
Maybe. So maybe I just know too much about alcohol, but the yeasts used in different beers, they're very tightly guarded secrets, because if you took a bread yeast and threw it into a random beer, it could taste absolutely awful because they make other things at the same time. And that's why Marmite can be made with different breweries' yeasts. I'm not sure if it tastes any different.
It tastes disgusting to me. But I did go and interview someone who's they're making a little portable lab. It's called the Bento Lab. And I think that one of the people using it is just sampling loads of beers to look at the DNA in the yeast and doing a project on that to work out if any beers are related to each other and to trace the yeasts back. So that would be a cool project, I reckon.
The trouble with small organisms is they do, of course, evolve. I mean, they change their genome a lot quicker. So if you try to do this on bacteria, you probably would have trouble trying to pick a pattern because you find things swapping and changing all over the place. And they do what's called horizontal gene transfer, where they don't just evolve in a linear progression. It hands a gene to its neighbour because they can.
Oh, yeah, they swap little bits of DNA, don't they? Because I did have this idea of going around all the recording studios and gig venues in London and taking samples from the microphones and just seeing what germs are going around.
Don't do it.
Probably best not to do that. But no, great question. Thank you very much. If you do have any questions for us or for a future show, you can tweet at Naked Scientists or you can find us on Facebook. Caroline, here's one for you from Leslie Wolfe. How do objects orbit in space?
So I like to think of this sort of like a ball on a string. So the ball is, say, a planet. The string is the force of gravity, and your hand that's swinging the ball around is the sun or whatever the orbiting object is orbiting. So say we're talking about a planet orbiting our sun. So the gravity attracts the planet at a perpendicular direction to its motion. So it keeps sort of travelling forwards, but getting pulled into the sun, but not quite fast enough to spiral in and crash into the sun. But it's also not travelling fast enough to get hurtled into space. If it were to slow down, it would crash into the sun. But because there's no particles, there's no air resistance, so the planet keeps going and, doesn't crash into the sun, doesn't fling off into space. It's kind of in a perfect, happy medium.
Is it Newton's? I can't remember whose example originally of firing a cannonball to explain it. And just if you had fired a cannonball fast enough, you could get it into orbit. And that's
Yeah.
the principle of spaceflight, basically. You fire something up fast enough and the Earth falls away faster than the thing falls back into Earth.
Yeah, exactly. So the cannonball's falling towards the Earth, but the curvature of the Earth is such that it can never actually land. It just kind of keeps going. And that's exactly the same principle as with planets orbiting the sun and moons orbiting planets.
So I was wondering, with these orbits, how do we get so many planets having exactly the right speed to orbit? Because I would have thought loads of them would just fall in the sun and loads of them would shoot off.
Fall sunwards, you start travelling faster, and therefore you can find yourself travelling fast enough to stay in orbit.
So it self-corrects.
I think so, yes.
And when was the solar system formed?
When was it formed?
yeah.
4.6
That's
billion
it.
years ago.
Yeah.
And there were lots of planet-sized bodies originally. We call them planetary embryos, and they would crash into each other. So it's very difficult to define the age of the Earth, because which of these parent bodies do you regard as the proto-Earth? So until you've got a body that's almost an Earth mass, you haven't got the Earth. But it all happened within 10 or no more than 100 million years at 4.6 billion years ago.
Wow, so then that's everything just accreting together.
It's
from all
starting
the-
off as gas and dust, and the particles bump into each other. They're fluffy, they stick together, they get bigger and bigger. Then they get enough gravity to start attracting each other, and then you've got runaway growth, and it all kind of speeds up.
So fantastic. I had a question here which I'm going to answer from Angelo Adato, who says, our cells are dividing all the time, billions of times. There must be many mutations during these divisions, and some of these will get propagated. Do we have areas of our bodies with different genetics? And this is a fantastic question, because the answer is kind of yes. We will pick up mistakes, changes, mutations, whether that's from the processes of life, like copying DNA, or from the oxygen that we're using to make energy. That damages DNA loads and loads and loads. Also, there are chemicals in the environment, and things like ultraviolet light, chemicals in tobacco smoke that can damage the DNA in different cells, and that can be propagated if those cells divide. So yeah, we are made up of probably little bigger or smaller clumps of cells that are all very, very slightly different. And obviously a good example of where this really goes wrong is cancer, because that's when cells have picked up a number of mistakes that have made them start growing out of control. Andrew, wrap your ears around this question from Chuck.
What's the difference between earwax and beeswax?
I love this. Come on.
So the main difference is don't eat earwax. Waxes are generally made of long hydrocarbon molecules, oils and fats, and the main one in beeswax is a combination of the product of a fatty acid and an alcohol. So that's what gives most of its waxiness. And actually, it's not too dissimilar what's in the ear. And I was trying to work out what the best defining feature is why you wouldn't want to eat one and eat the other. Because the smells are really just due to what impurities make it up. The main difference I could come down to was that beeswax sort of makes these lovely honeycomb structures, and they then put honey in them, and the bees secrete to make it. Your ears make earwax to pick up dead cells, bacteria, and hair. And that really is the difference. So you get quite a disgusting thing out your ear where you get honey from the beehive.
Lovely.
But the wax is fairly similar.
There's two types of earwax as well, isn't it? There's like wet earwax and dry earwax. So you couldn't make a candle out of either of them.
I think you can. In fact, I'm sure you can.
Oh my God.
It just don't.
Christmas present ideas.
And that difference in melting temperature, depending what ratio of the different waxy chemicals you use to make it. But effectively, a wax is just an oil that has a melting point above room temperature, so it solidifies.
Ew, that is a completely disgusting thought. You're listening to The Naked Scientists with me, Kat Arney. Caroline, Ari has sent in a rather charged question. He says, if my car gives me static shocks, why is it a good idea to be in a car during a lightning storm? Well, is it, for a start?
It is a good idea to be in your car in a lightning storm. So static shocks happen when two materials rub against each other and charge transfers from one to the other. So this could be when you're sat in your car wearing some sort of synthetic material and it rubs against the car seat and you build up a negative charge, and then you innocently reach out to grab your car door handle and the negative charge from you discharges through the car and makes a sort of nasty shock. But lightning, it's a good idea to be in your car if there's a lightning storm, because if lightning were to strike the outside of your car, the lightning would travel through your car body and not actually harm you. And that's because the car, well, provided your car is made of metal, the current will want to travel through that because current likes to go through the path of least resistance. So it will travel through the car to the ground, shielding you. And this is often referred to as a Faraday cage.
And you've got rubber tyres as well. Is it something like you meant to wear wellies as well in an electrical storm?
So the rubber tyres thing is quite often... it's a bit of a myth. It's an easy answer to why you should get in your car, but that's not really why, because the current does still flow through the tyres to the ground. It does discharge. But yes, if you're wearing rubber shoes, rubber's an insulator, so you're slightly more protected from an electric shock because it makes a bit more of a resistive path for the current to travel, and it's less likely to travel through you.
Adam?
How do I stop getting shocked by my car?
You could buy a non-metal car.
Good. Yes.
Which is an option.
For Robot Wars.
Yeah. Or you could wear clothes that sort of build up static charge less. So, when you the cheaper more plastic clothes build up static charge more.
Are you wearing nylon? So
yeah,
stop wearing the
nylon's
nylon 90s.
I remember I used to have a dressing gown that I could build up such a static charge on by rubbing it against the carpet that if you turned off the lights, you could actually see the little electric discharge if you touched it.
Okay,
so don't wear that dressing gown.
No driving in my dressing gown.
Yeah. No driving in dressing gowns. Go for sort of... I'm not sure what materials are not good
Linens,
at building up charge.
cottons,
Imagine sort of stuff like silk and things like that would be fine. So
silk,
just get a silk
silk
suit,
trousers.
silk suit, and a wooden car, and you're absolutely fine.
No chances of electric
Thanks very
shocks. Okay, we've got one more question, which we can have a little guess at, but I think I'll ask everyone. But Donald wanted to know, how many new cells does a person produce every second? So we'll get everyone to have a little go. And then what do you reckon? How many new cells made in the body every second?
You're looking at me. You want me to guess?
Yeah, I want everyone to have a guess. Come on.
There's billions of cells in our body, so we're probably making hundreds of thousands every second.
Hundreds of thousands?
10 to the 5.
Adam?
Oh, but now we've got one guess. All of our guesses are going to be basically the same, right? Because we've anchored the guessing. I'm going higher.
You're going higher, okay. Andrew?
I feel under a lot of pressure right now.
You're a biologist.
Yeah, this is not my field of biology. I'm going for 1 million.
You're going for a million cells per second?
I'm going to go for lower. I think, because I remember reading somewhere that you do retain some cells for quite a long time. So I'm going to go for tens of thousands rather than hundreds of thousands.
So I've been doing a little bit of maths. Maths is not my strong suit, but I have been having a little go at this. And your whole body is made up of, probably now the best estimates are around, there's 37 trillion cells in your body. And as Caroline is right, some of your cells don't multiply very often. Things like your heart muscle doesn't really multiply. But then cells like your skin cells, your immune cells, your red blood cells, your gut cells, sort of the epithelia, they really, really, really multiply. And it turns out every single day, roughly 50 billion cells in an adult will die. Okay, so your 50 billion of your cells die because there's this turnover. You've got to make new cells, got to keep repairing, got to keep, renewing. And so I think every second there's about 2 million red blood cells made. You'll also have cells being made in your gut, in your skin. So it works out, probably if you do the sums, if about 5 million cells are dying every second, it's probably about that many being made every second as well. It's like something like 40,000 skin cells in a minute, which always makes my flesh crawl.
Gosh, I lost that one.
A tiny bit. No, there's no winners and losers. Only science is the winner in this one. We've got a really, really quick tweet from Ed Wilson. He wants to know, how can a hydrogen atom be said to be with certainty 13.7 billion years old? Does a proton always have the same electron?
No, it doesn't.
It doesn't. So
the nucleus will be that old, but it can gain its electrons and lose it, and
we get into the sort of philosophical, like, what is an atom? Is it like always do you step into the same atom twice?
I'd imagine there's not many hydrogen atoms that have kept their same electron for 13.7 billion years. I mean, and also I'm not really sure how you'd test it. I don't think you can. I think it must be speculative, really.
Yeah, that you can't identify an individual electron.
You can't fingerprint an electron.
No.
But at the state of the universe in the early days, the nuclei and the electrons would have been separate.
Wildly promiscuous swapping of electrons. Thank you very much. That is it for this week. Thanks to our guest panel, Andrew Holding, Caroline Steele, David Rothery and Adam Townsend. The programme was put together by Chris Smith. We're back next week with a look at the evidence behind education. Are we teaching young people the right way? And what role might their genes play? The Naked Scientist comes to you from Cambridge University and is supported by the STFC, the EPSRC and Rolls-Royce. Thanks for listening, and until next time, goodbye.